Turns out we can use this gradient vector to come up with the tangent plane equation. But it hinges on this important fact here, and that is the gradient vector at x0, y0 is orthogonal to the level curve f of xy equals k at the point x0, y0. Okay, so yeah, this gradient vector is orthogonal to that level curve at that particular point. That will provide a helpful little nugget right there. And then you can also go three variable gradient. That's also orthogonal to the surface, the level surface. We didn't do any. We did some level curves, but we didn't get into level surfaces because it's a whole other fun deal. But anyway, the gradient vector is orthogonal to the level surface f of x, y, z equals k at x0, y0, z0. So same sort of relationship. It is orthogonal. Now, that again can be shown through well, basically through the dot product between the gradient vector and the derivative vector for your curve. The dot product 0 is what it amounts to. Remember that the dot product 0, then they're perpendicular, orthogonal. That's what you call them in vector form. But with that particular fact, let's revisit our tangent plane. All right, so remember, just in general, the equation of a plane. What do we need? Well, we need a point, so equation of a plane through a point, x0, y0, z0. And we need, remember, we also need a normal vector. We just denoted ABC in normal vector. All right, and so that gave us a way to write down this equation. It turned out it is then, the equation of the plane is, so you take the A times x minus x0 plus then the b times y minus y0 plus c times z minus z0. So set that up and equal it to 0. That's going to be a plane. So if we know point and normal vector, so you need those two things. Well, say we have a function So we're talking a tangent plane to our surface, to the surface, given by f x, y, z equals k, equals a number. And we're going at the point x0, y0, z0. All right. Well, okay, so we've got the point, right? So we're looking for a plane. Now, the key ingredient here is we're talking a tangent plane. And we know, we also know something about, so we don't have the orthogonal, the normal vector here, but what we do know, what's our normal vector here going to be? Well, that's where our gradient comes in, because what we just talked about, the gradient of f at a particular point, that's orthogonal to the surface. Well, orthogonal is what we're looking for. The normal vector, remember what we're talking about for a plane, the normal vector is that vector that's, orthogonal. It's orthogonal, so it's 90-degree angle to the whole entire surface there. And so we just so happen to have a orthogonal vector. So our normal vector is that gradient vector, okay? And so the gradient of f x0, y0, z0, I said write that, but yeah, you're just going to do the partials. In this case, I'm talking three partials there. So that's going to be our A, B, and C's. Right? A, B, and C are just, A is going to be the partial with respect to X, B is going to be the partial with respect to Y, C is going to be the partial with respect to Z. And so that tangent plane then, all right, so it'd be so it'd be F with respect to X at, whatever point we're talking about, times X minus X0, plus then the B is the partial of F with respect to Y, and then this C is the F partial with respect to Z. Right out. So, yeah. That gives us the tangent plane for this, just that surface. F of x, y, z equals some number. Okay, so let's do one of those. All right, so let's find the tangent plane of x squared plus y squared plus z squared minus 30 equals 0 at point 1, negative 2, 5. Just kind of shorten it down a little bit. So this tangent plane, all we have to do here is just basically we need to get our gradient and evaluate it, you know, at our particular point here. So this is dx0, y0, z0. So these are pretty easy ones, partial anyway. They're all just 2x, 2y, and 2z, right? Easy enough to do the partials there. All right, so again, we want to evaluate that at the particular point we're at. So 2x, we're going to evaluate that at x is 1, so that would be 2. And then x minus x0 will be 1. Then we do the partial of y at the particular y value, so in this case it's negative 2. So that would be negative 4, the f of y, times y minus negative 2, so plus 2. And then the partial of f with respect to z at the z value would be 10. Z minus 5. There you go. And arrange that, however, it would probably, probably go 2x minus 2 minus 4y minus 8 plus 10z minus 50. They'd probably go ahead and get the x, y, z on one side, then what else we got? Minus 60. Either that or move that 60 over, add 60. So one of those two would probably be the best way to go on that. Another way to do a tangent, tangent plane there. All right, then they also, we also talked about normal lines. It's almost kind of like a 2-for-1 deal with this gradient vector. Remember, for an equation of a line, we need x0, I need a point. Three-dimensional here. And we need a parallel vector. ABC. So ABC here, we're talking be parallel. Well, we're, and if that's the case, then remember the symmetric form, there's different forms, but this is the form they choose here. The symmetric form of then the equation of the line, you do x minus x0 divided by a, and then y minus y0 divided by b, and then equals z minus z0 or c. That's the way they choose this one to go with this one. You know, there's other forms, the parametric forms and all that, but whoops, I should let this up here. Well, where that comes in here, all right, so what can I get out of my gradient vector? Say I've got, I want the normal line to our surface here. F x, y, z equals some constant at x 0, y 0, z 0. All right. Well, again, since I know that the gradient vector at x 0, y 0, z 0 is, so the normal line, that's, you know, the line that's perpendicular at a particular point to our surface. So that if I want a normal line to that, well, the gradient vector would be parallel to this normal line. It's perpendicular to the surface, so it's parallel to the normal line. You see what we're saying? So that's orthogonal to our surface, and so hence we can use that for our parallel vector there in our equation. So we can use it for the vector for the normal line. So hence, then, the normal line is going to be x minus x0 over, all right, so the a, so our gradient vector is, the a is partial of f with respect to x, the b is partial of f with respect to y, the c is partial of f with respect to z. And so that's our A, B, C. So you're just gonna, for the normal line, your values for your directional, values for your partial derivatives, you're just gonna put those as the denominators in your symmetric form anyway. I always convert it to some other form. So going back to that other one, finish it off here. Okay, so the normal line to x squared plus y squared plus z squared minus 30 equals 0 at 1, negative 2, 5. Well, it's going to be x minus x0 is 1, divided by the partial derivative. All right, so I erased them, but it was pretty easy anyway. 2x, 2y, 2z, partial derivatives. So now I want to evaluate, so what goes here is the partial of f with respect to x evaluated at that point, so that'd just be 2. Y minus y0, so it'll be y plus 2 over partial of f with respect to y evaluated at the point, so that was negative 4. And then z minus z0, so it'd be z minus 5 over the partial of z, partial of f with respect to z, so that'd be 10. So that's going to be the normal line right there. So it's kind of, like I said, it's kind of a 2 for 1. That was the same equation there that I did the tangent plane for in the same point. So basically you get a 2 for 1 here. Good.